Would you like to know how to use food as medicine for your genes? Get access to my free webinar using the link in the video description. I hope you enjoyed the webinar, and if you do, please make sure to comment and share.
Now, one of the main focus now is for us is the mitochondria. Okay, and why? And one of the reasons is that if many times that I did the analysis of pathway analysis of the genes that are transgenerationally altered, one of the top hits was always mitochondrial pathways. Okay? And if you read papers that talk about metabolism disruption and they check genes altered in terms of gene expression or epigenome, mitochondrial pathways are always there on top. They're always being shown as important ones. And in addition to that, there is this inheritance aspect, right? That mitochondria is mostly inherited from mothers to the offspring. And as I said, there are a lot of research here showing the mitochondrial dysfunction is related to diseases, but mainly these diseases that I have told you, metabolic and reproductive diseases. Mitochondrial dysfunction, for example, is related to poor quality egg, okay? And is also related to aging, diabetes, insulin resistance. Now, the question is, if mitochondrial function can be programmed, how is that happening? And obviously, here we think, well, mitochondrial epigenome, right? So that's why we, in addition to studying the mitochondrial ability to be programmed, we're also in parallel studying the ability of mitochondria to be differentially methylated in response to early environmental exposures. And I will show a little bit of like what are we doing with the gene, what are we measuring here. So basically we're measuring the mitochondrial epigenome. Yeah, this is the method we intended in the beginning, but we are, just to make it clear, we have not measured yet. We're in process of measuring the mitochondrial epigenome, but we have just finished measuring the mitochondrial function using this very cool machine that measure different stages of mitochondrial respiration. It's called the Ouroboros machine. We have taken electronic microscopy pictures of this mitochondria in different conditions, and this is what I'm going to show you now. And we also have data on the whole resting metabolism of these animals. So basically, with chickens, you can put them, they sleep really well. You put them inside like this little chamber during the night. They don't wake up, so that you are able to measure during the whole night how much oxygen they consume in this resting state. Okay, so we're comparing resting metabolism after exposure, early development exposure with these conditions that I showed. Now, one of the first things we observed here was the heart. Okay? We observed that in the female heart at the age 64, 69, so, and again, exposure here to this thing, these different conditions was only during the egg. Okay? And then the animals were sacrificed later on, and we see here the heart weight is already affected in these animals. So heart weight is already, different heart weight in the adult is already programmed by these environmental exposures later on. And not only total heart weight, but also heart weight relative to the body. But not only that, we started to observe these heart lesions, these lesions in the heart. And I mean, if you have seen a chicken heart, a normal chicken heart is shiny. It looks very beautiful. It's red, shiny. And you can see this heart is dried and has these lesions, this sort of cuts. Okay, so this is a big difference in health in these animals when they're adults, after they have been exposed to, one of these conditions here was hypothermia. And as I mentioned before, we also checked mitochondrial morphology and number. Okay? And this was done with image J. So basically, we had the work of master students and my postdoc, John Lees. So what they did, with image J, they set the limits of they draw the limits of the mitochondria, and they calculate length and width, and then they calculated the area of this mitochondria. But not only that, they counted the mitochondria per section observed in different sections. And they observe that, you see here, that the mitochondrial area really goes down with this early environmental exposures. So mitochondrial area is a factor that is already programmed by these environmental exposures. Now, what is even more interesting is this reduction in mitochondrial area is compensated by an increase in mitochondrial number. Okay. So this is just initial data that we have, but we will have a lot of data on how we correlate these mitochondrial features with the mitochondrial function. Okay, so we want to see whether this compensation at the end brings the mitochondrial function to equal. So basically, maybe nothing happens in terms of mitochondrial function, but we will know that soon. And with this, and this is our representative macroscopy photos. So you can see here, and they are the same size, 2 micrometers. Okay? And you can see here to the left how these mitochondria, they are round and they're big in the control heart, but in these 2 treatments, how they are much smaller and much more numerous as the numbers show, right? So this is just representative images of the same data that I have shown. And with that, yeah, I want to finish this the last of our research on this, on the programming of metabolism. And I want to show my group here, my 2 postdocs, Fabio and John. Manolis, which I think he's also there connected. Farnas, so she's connected too, my PhD student, and another PhD student, Violetta.